Hi students, good day. Laplace transformations. We are covered so many sessions on Laplace transformations. Today, particularly Laplace of t f of t is equal to minus d by ds of Laplace of f of t. So we have to prove these results. Okay. So let Laplace of to prove, and I am going to solve one problem also by using this Laplace of t f of t can be written as d by ds of Laplace of f of t. Okay. And in previous sessions, capital F of s is used for Laplace of f of t. No? Yes. Laplace of f of t usually in this chapter Laplace transformations is denoted by f of s. Okay. So for getting this result, I introduce d by ds on both the sides. So d by ds of f of s here is equal to d by ds of Laplace of f of t, and d by ds of, Laplace of f of t is nothing but integral 0 to infinity e power minus st dot this f of t dt. We know that Laplace of f of t is e power minus st f of t dt with the integral 0 to infinity. Yes. Here s and t are independent variables, s and t. But we have to differentiate this expression with respect to s. So I can send this d by ds, because of two variables are available here, I can send this as dou by dou s, partial derivative of e power minus st. Here nothing is available for s, so I can close this bracket. F of t dt is separate. Now integral 0 to infinity dou by dou s is differentiation with respect to s, partially derivative e power minus st, and for minus st with respect to s, minus t will come into f of t dt. Yes, is equal to integral 0 to infinity, I can take minus outside, e power minus st dot t f of t dt. Remember, this Laplace of f of t is integral 0 to infinity e power minus st f of t dt. Okay. Suppose integral 0 to infinity e power minus st phi of t dt is available, means Laplace of phi of t is the answer, Laplace of phi of t. So e power minus st is available, t f of t instead of phi of t, here t f of t is available. So this is called or this can be expressed as Laplace of t f of t. So d by ds of capital F of s is available on left hand side, minus I can rewrite once again here 0 to infinity e power minus st t f of t dt. This format is nothing but minus Laplace of t f of t. Okay. Therefore Laplace of t f of t is equal to, I can bring this minus this side, minus d by ds of capital F of s. Capital F of s is nothing but Laplace transformation of f of t. Okay, so, this is the proof of this question. The proof of see here Laplace of t f of t equal to minus d by ds of Laplace of f of t. So for example, one question, Laplace of t cos at. Here t is t. For f of t, here cos at is available. So this is nothing but minus d by ds of Laplace of cos at. In earlier sessions, we derived the Laplace transformation of cos at. Laplace transformation of cos at is s divided by s square plus a square. Now we have to differentiate with respect to s. Quotient rule. Quotient rule means v u dash minus v u v dash divided by v square. Quotient rule, u by v. U by v method or quotient rule. Here s square plus a square whole square for v square. V is s square plus a square into differentiation of s is 1 minus, according to the rule, u is s and differentiation of s square is 2s, and for a square is arbitrary constant, so we can leave that derivative of any constant becomes 0. Then I can close here. Is equal to minus s square plus a square whole square is denominator, 1 into s square, 1 into a square, minus 2s square is equal to minus of minus s square plus a square by s square plus a square whole square is s square minus a square. By sending this minus inside, no change in denominator, as s square plus a square whole square. Yeah, so this is the derivative format of t cos at. So Laplace of t cos at is minus d by ds of Laplace of cos at. The result is available here. Similarly, you can practice more problems f of t with the t problems, and next session we are going to learn t square, t cube and more. Thank you.